Hello learners, on behalf of Indira Gandhi National Open University, we welcome you for this video lecture session. Today's topic is Vapor Compression Refrigeration System. This is 36th module of the course Thermodynamics and its application. I am Subhashish Maji, professor in School of Engineering and Technology from Indira Gandhi National Open University. So, dear learners, let us begin our today's discussion on vapor compression refrigeration system. After listening to this video lecture, you will be able to understand the concept of vapor compression refrigeration cycle. You will be able to know the types of refrigerants. You will be able to explain the performance of vapor compression refrigeration cycle. You will be able to describe the capacity of vapor compression refrigeration cycle, and you will also be able to solve the numerical related to vapor compression refrigeration cycle. Refrigeration is the process of maintaining a body or a zone in space at a temperature lower than the local surrounding temperature. Hence, refrigeration requires the continuous transfer of heat from the body or the zone to be refrigerated to the surrounding at a relatively high temperature. It has been explained in earlier discussion that such a job can be done by a reverse heat engine. However, this is not the only method available for providing refrigeration. There are several other methods used in practice. The most commonly used methods are vapor compression refrigeration system, gas compression refrigeration system, vapor absorption refrigeration system, and steam jet refrigeration system. A vapor compression refrigeration system is used in a majority of cases where refrigeration is required for different purposes. Its popularity is mainly because of its high performance characteristics and trouble-free working for long period of time. Shown in figure 1 is the schematic of a simple vapor compression refrigeration system. In short, we will say VCRS, vapor compression refrigeration system. This is essentially the same as that explains the working of a refrigerator. Here, the working substance called the refrigerant undergoes a thermodynamic cycle while transferring heat from the low temperature reservoir to the high temperature reservoir with the help of external work. This is the diagram for vapor compression refrigeration system. Here you see that there are 4 important components for this vapor compression refrigeration system. First one is evaporator, where cooling of the refrigerated space is going on. There is compressor, there is condenser, and there is also expansion device. So, we will discuss in detail the functions of each component, that is evaporator, compressor, condenser, and expansion valve. So, point 1 is the exit point of the refrigerant from the evaporator as well as the entry point of the refrigerant in the compressor. Point 2 is the exit point of the refrigerant for the compressor, and point 2 is also the entry point of the refrigerant in the condenser. Similarly, point 3 is the exit point of the condenser, and point 3 is also the entry point of the expansion device, and point 4 is the exit of expansion device. Point 4 is also the entry point of the evaporator. So we will discuss each and every component's functions in detail. The VCRS shown in figure 1 has 4 major components, namely the evaporator, the compressor, the condenser and the expansion device. The ideal or the basic cycle on which such a system operates is shown in figure 2 on both TS diagram and pH diagram. TS means temperature entropy and pH means pressure enthalpy. So this is the VCR cycle for the process. Here you see that point 1 is the entry point of the compressor, point 2 is the exit point of the refrigerant which is coming out from the compressor, and 2 to 3 is the process going on in the condenser, and 3 to 4 the expansion process, and 4 to 1 is the net refrigerant effect during this process which is occurring in the evaporator. Now we will discuss in detail for the process which is going on in the vapor compression refrigeration system. Wet refrigerant vapor at state 1 from the evaporator enters the compressor. This vapor is compressed reversibly and adiabatically to saturated vapor at state 2. Let the work required by the compressor be W. At state 2, the pressure is equal to the saturation pressure of the refrigerant corresponding to the condenser temperature. The high pressure vapor at state 2 is condensed to saturated liquid at the same pressure as it passes through the condenser, and let QH be the heat transfer from the refrigerant to the surrounding at temperature TH. The saturated liquid at state 3 is then throttled through the expansion device to low quality vapor at state 4. At state 4, the pressure of the refrigerant vapor corresponds to its saturation pressure at the evaporator temperature. This low quality vapor, as it flows through the evaporator, picks up heat to maintain the refrigerated space at a temperature TL, and then leaves it at state 1 as a high quality vapor. Let QL be the heat transferred to the refrigerant at the evaporator. The design of vapor compression refrigeration system is greatly influenced by the properties of the refrigerant used in the system. The most widely used refrigerants are the halocarbons of the freon family. The chemical composition of each halocarbon in the above family is identified by the number ascribed to it. For example, the commonly used refrigerant in the domestic refrigerator is freon 12 or R12, which is nothing but dichloromethane. Formula is CCl2F2. Similarly, freon 22 or R22, which is commonly used in window air conditioners, is monochloro-difluoromethane. The formula is CHClF2. The other refrigerants in the family are R11, R13, R14, R22, R113 and R114. The selection of the refrigerant depends upon the evaporator temperature needed, the type of compressor used in the system and the capacity of the system. it is not always the halocarbons that are used as refrigerants. Many inorganic substances such as NH3, that is ammonia, H2O, air, CO2 and SO2 are also used as refrigerants in certain specific situations. Properties of the refrigerant are available in the form of tables similar to steam table or charts in handbooks on refrigeration and air conditioning. Performance of vapor compression refrigeration system. The performance of a vapor compression refrigeration system is expressed by its coefficient of performance. Coefficient of performance of a refrigerator is defined as heat transfer to the refrigerant at the evaporator divided by work input. For this case, COP is equal to QL by W because W is work done onto the system and QL is the net refrigeration effect. But while applying the first law of thermodynamics, we can say that W is equal to QH minus QL. So COP, that is coefficient of performance of the vapor compression refrigeration system, is equal to QL divided by QH minus QL. Performance of vapor compression refrigeration system. The following relations that gives the magnitude of heat and work interactions may be obtained by the application of steady flow energy equation based on unit mass to the four components of the VCRS. The state points marked on the schematic, that is on figure 1, and the cycle diagram, that is on figure 2, are compatible. So QL, that is equal to H1 minus H4. Here this is the net refrigeration effect. W is the work done by the compressor, that is equal to H2 minus H1. QH, that is heat given out by the refrigerant to the surrounding in the condenser, that is equal to H3 minus the QH is the heat given out by the refrigerant in the condenser, that is equal to H2 minus H3. But when you talk about the expansion process, when the refrigerant is passing through the expansion device, the enthalpy before and after the expansion process will be same. So during the throttling process, H3 is equal to H4. Now if you put all these expressions for the COP, that comes out to be equal to H1 minus H4, that is the net refrigerating effect, divided by the work done by the compressor, that is equal to H2 minus H1. So this equation you can rearrange as COP equal to H1 minus H4 divided by H2 minus H3 minus within bracket H1 minus H4, because H3 is equal to H4. Now let us discuss about the refrigerating effect. In the evaporator, the heat is taken away by the refrigerant from the confined space. Why? Because while passing through expansion device, its temperature and pressure will become very low for the refrigerant, and that low temperature for the refrigerant is sufficient to extract heat from the confined space, which is to be refrigerated, because heat will always flow from a high temperature region to a low temperature region. Now after that, in the compression, in the compression process, the pressure and temperature will increase. That high temperature, high pressure refrigerant will pass through the condenser and it will always flow from high temperature body to the low temperature body. That's why heat will flow from the refrigerant to outside the condenser during the process which is going on inside the condenser. So here the net refrigerating effect is equal to H1 minus H4, unit is kilojoule per kg. Capacity of the VCR. The capacity of a vapor compression refrigeration system expressed in kilowatt is the rate at which cooling is produced in the evaporator. Therefore, capacity is equal to mass flow rate of the refrigerant multiplied by net refrigerating effect. So capacity we can write equal to M multiplied by H1 minus H4. Obviously its unit is kilowatt, where M is in kg per second and H is in kilojoule per kg. This is, now let us talk about the ton of refrigeration. This is the unit of capacity of the refrigeration system commonly used in British system of units. A refrigeration system is said to have a capacity of 1 ton if it can provide cooling at a rate of 200 BTU per minute. This is so because of a system cooling at this rate can completely freeze 1 ton, that is 2000 pounds of water at 32 degree Fahrenheit to ice at the same temperature in a day, that is in 24 hours. This can easily be checked assuming the enthalpy of fusion of water to be 144 BTU per pound. Now capacity is equal to cooling produced divided by time taken. So 1 ton capacity is equal to 2000 multiplied by 144 divided by 24 into 60 is equal to 200 BTU per minute. Because of its long time continuous use in the refrigeration industry, this unit of capacity has come to stay and is used widely everywhere irrespective of the system of units used. It is advised not to use this unit of capacity in SI system of units. Here the capacity is best expressed in kilowatt. However, to have a feel for the relative magnitude of 1 ton and 1 kilowatt, the following conversion factor can be used. 1 ton is equal to 200 BTU per minute equal to 3.5 kilowatt. So we can say that 1 ton is equivalent to 3.5 kilowatt of cooling effect. Now capacity of refrigerator in SI system of unit. It is the rate at which heat can be extracted from cold body, the rate at which refrigeration can be produced. It is defined as the quantity of heat removed to freeze 1 ton of water at 0 degree centigrade to ice at 0 degree centigrade in 24 hours. So 1 ton of refrigeration is equal to 12,600 kilojoule per hour equal to 210 kilojoule per minute equal to 3.5 kilojoule per second. Now compressor power. This is the power to be supplied to the system from the surrounding. So compressor's work is equal to H2 minus H1 because it is a process from state 1 to state 2. So power is equal to mass flow rate of the refrigerant multiplied by watt per kg. So power is equal to M multiplied by H2 minus H1 and unit is kilowatt, where M is in kg per second and H is in kilojoule per kg. Now let us talk about wet and dry compression. The basic or ideal cycle for vapor compression refrigeration system shown in figure 2 is called the wet compression cycle. Because the condition of vapor at inlet to the compressor is wet, shown in figure 3 is the basic cycle on TS and pH diagram for the dry compression cycle. Here the vapor enters the compressor as saturated vapor at the evaporator temperature. The dry compression is normally preferred mainly for the following two reasons. The compression efficiency is high and no damage to the compressor by the entering slugs of liquid. Dear learners, please look at the cycle diagram for vapor compression refrigeration cycle. So this is for dry compression because one is the entry point of the refrigerant in the compression. So you see that point 1 is on the saturated vapor line. So it is the case of dry compression, and 2 is the exit point of the compression process. So this is the cycle diagram. So in this case you can see that net refrigerating effect is H1 minus H4. The compression work done is H2 minus H1, and the heat rejected in the condenser is equal to H2 minus H3, and here H3 is equal to H4 because this process is going on through the expansion device. In the absence of any specific information in the analysis of a simple vapor compression refrigeration system, the system is assumed to work on basic or ideal dry compression cycle shown in figure 3. In such a case, the vapor at entry to the compressor is saturated vapor at the evaporator temperature, and the compression of this vapor to state 2 through reversible and adiabatic compression in the compressor. Also at state 2, the pressure is the saturation pressure of the refrigerant corresponding to the condenser temperature. In actual practice, the cycle do not strictly follow the basic cycles because of irreversibilities. Also, many modifications are made on the basic or ideal cycles to improve the system performance. Explanation of all these improved cycles is beyond the scope of this course, and hence the reader is advised to look into standard books on refrigeration for further details if required. Now let us discuss a very interesting numerical. The COP of a wet compression ideal vapor compression refrigeration system of capacity 5 tons is given to be 3. Work supplied to the compressor is 20 kJ per kg. Find the mass flow rate of the refrigerant and the refrigerating effect. So we know very well that COP is equal to net refrigerating effect divided by work input. Here COP is given as 3 equal to NRE, that is net refrigerating effect, divided by work input. Here work input is given 20 kJ per kg. So net refrigerating effect comes out to be 60 kJ per kg. Now we know very well that capacity is equal to mass flow rate into net refrigerating effect. So mass flow rate is equal to capacity by net refrigerating effect. So mass flow rate is equal to 0.2917 kg per second. Dear learners, we have discussed about the vapor compression refrigeration systems. In the vapor compression refrigeration system, there are four important components. One is evaporator, second one is compressor, the third one is condenser, and the fourth one is the expansion device. In the expansion device, when the refrigerant flows through the expansion device, there is a sudden drop of pressure as well as temperature. Why the temperature suddenly drops because of the low pressure? Because at the low pressure, some portion of the refrigerant which is in the liquid form immediately evaporates. Because of the evaporation, it takes the latent heat from the refrigerant itself. So it is a two-phase mixture whose temperature is much below for extracting heat from the space which is to be refrigerated while passing through the evaporator. So in the evaporator, heat is flowed from the confined space which is to be refrigerated into the refrigerant, because refrigerant temperature is low, outside temperature is high. Now after that, the refrigerant is passing through the compressor. In the compressor, what is happening? The temperature and pressure is increasing. The temperature will be such that it can transfer the heat while passing through the condenser to the outside. So heat is being transferred from the refrigerant to the outside, that is QH, and heat is taken from the refrigerated space while passing through the evaporator is QL, and work done on the compressor is the work done by the compressor is W. So we know the refrigerating effect, that is QL. We know the work done, so COP is equal to the net refrigerating effect by the work input. So this is the procedure for the vapor compression refrigeration system. Dear learners, we will discuss several types of refrigeration systems in our later discussion. So let us discuss a second important problem. What is the maximum COP of a VCRS operating between an evaporator temperature of -3 degrees centigrade and a condenser temperature of 27 degrees centigrade? Now we know very well that COP is equal to T2 divided by T1 minus T2, where T2 is the sink temperature, T1 is the source temperature. So both the temperatures are given. So COP is equal to 270 divided by 300 minus 270, that comes out to be 9. So COP for this numerical is 9. But dear learners, I have already mentioned that while putting the values of T1, T2 in the expressions for COP, you have to convert the centigrade temperature into Kelvin scale. Let us summarize our discussions very quickly. We have discussed the concept of vapor compression refrigeration system. We have discussed the types of refrigerants. So refrigerants are the substance which is circulating in the cyclic process, and that may be in liquid form in some cases, maybe in two-phase mixtures, or maybe in the vapor state. We have discussed the capacity of vapor compression refrigeration cycle. We have also solved some numerical related to vapor compression refrigeration cycle. Thank you very much.